Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and today's topic is algorithms. So, today we will be looking at something called sorting algorithm, and we will be specially looking at something called insertion sort. So, to start with, we will look at how to insert an element in a sorted list, and then using that algorithm as a sub tool. So, what is a sorting algorithm? So, we have been given a set of elements. Ideally, we should think of something in the set of some set of objects which has some total ordering in them. For example, the set of integers or set of numbers or set of words under the lexicographic ordering, and we want to sort the elements in this list. So, in this lecture and in subsequent lectures, we will assume that the set that we have been given is a list of integers or numbers. Although there is nothing special about these numbers, we just use them as some class of objects which has total order. You can replace them with say set of words or some other objects which has total order. For example, consider this set S. Let this S be a set of integers which is 1, 4, 2, 10, 5, 8, 15, 13, 7, 8 and 1. Now, the goal is to sort these elements in this set. Now, this set is just a collection of integers, and we know that integers have a canonical ordering, that is 1 is less than 2, 2 is less than 4 and so on. So, what do we want? We want an algorithm that will output something like this. Note that it has the same set of elements as it was in the original set S, except that now these elements are sorted in an ascending order, thus 1, 1, 2, 4, 5, 7, 8, 8, 10, 13 and 15. It is just exactly the same set of elements that was there in this set, just has been sorted in the ascending order. So, this is our goal. So, we will be given a set S and we want to sort them and output the sorted list. Now, this is one of the most well studied problems in algorithms, and here is just a sample of some of the sorting algorithms that are there in the market. This is by no means a complete set, and under various circumstances some particular algorithm is better than some other algorithm and so on. We will be looking at just a handful of them, actually 4 or 5 of them from this set, and talk about which algorithm is good for which purpose. So, this is what we will be doing in the next few lectures. So, in today's lecture we will be looking at insertion sort. So, what is insertion sort? So, before we go into insertion sort, let us look at the sub problem, which is how to insert an element in a sorted list. So, we have been given say as set S of n integers, and we have also been given another element x. Now, this S is already sorted. So, it is a sorted list, and now we want to insert this x element x into this set S at the right place, so that after I insert x, the resulting set is still sorted. So, what is the first step for doing this kind of stuff? The first step of course is we have to find the place where x should go. Note that S is a sorted list. So, there is a particular place where x should go, like x should be right of any element which is smaller than x and left of any element that is greater than x. And we have seen this one in our last lecture or last couple of lectures, that we can use exhaustive search. Like you can go over the whole set one by one, elements in the set one by one, and then find out the exact place where the element x should go. This is the exhaustive search, and we saw that in the worst case it has a runtime of n. That means, we might have to go through the whole list before we can find out the exact place. Other one is the more interesting algorithm, which is the binary search, where you can do some clever way of searching, and using just log n comparisons we can find out the place where x should go. The catch is that this exhaustive search can be done on any set, however way the set is given, but the binary search can only be done when the set S is given in the random access memory model. So, this is the first step of insertion an element x into an set S. So, now let us see how to insert an element. Let us look at two techniques. In the first technique, let us assume that the set is this sorted set S, 1, 1, 2, 4, 5, 7, 8, 8, 10, 13 and 15, and let the number that we want to insert is this number 6. So, now let us assume that the set S is given in the linked list model. So, it is not given as a random access memory model. If it is not given in the random access memory model, then binary search will not do, in which case to find the position of 6 we have to do an exhaustive search. So, we find the exhaustive search, we use exhaustive search to find the right place for this element x. Say in this case, since we are assuming that it is in a linked list model, for people who are not used to linked list, it is a data structure model where we store each element in a place along with an address to the next element. So, we say that we have placed 1 and then there is a pointer that says where is the next element, which is the next one. Then we again stored this element 1 and a pointer to the next element where the element is kept, which is 2, and so on. So, in the linked list model, we assume that the set has been given as the linked in terms of this element and its arrow to the next element. Now, here where is the number 6 should go? It is not hard to see that number 6 should go between 5 and 7. Exhaustive search will find it out. Now, what we have to do? We have to somehow insert this element 6 in this place. Note that in the linked list model, this insertion is very easy. All we have to do is remove this arrow from 5 to 7, instead put an arrow to 5 to 6, and from 6 I put an arrow to 7, and that would make it into a linked list. So, what we can do is we can get something like this. This is very simple. To put the number 6 into this list, we required almost no step. So, the total runtime is n for the exhaustive search and 2 for inserting this number 6 in this sorted list. So, this is the technique 1. Now, comes the point, can we do better? For example, we know that binary search can find the right place of number 6 or whatever element in just log n steps. Can we use that binary search to get a algorithm better than n, runtime n, to insert an element x into this list. So, here we have the technique 2, which is we have been given this array, this set as an array, which is a random access memory. Note that our idea is to use binary search. So, we need to have this set given in a random access memory, and we consider the same set S, and we have the same x, which is 6. And again, using binary search, we can now find out the position of the number 6 in this array, which is between 5 and 7. Note that here, to find the position, right position of the number 6, we only require log n number of comparisons. So, it seems that we are making a good progress, because in the last technique it took us n number of steps to find the right place, and now it just takes us log n number of steps to find the right place. But there is a catch to it. This set has been given as an array. So, it is inserting this element 6 into this array is not as simple as in the earlier case. It is not like I put an arrow from 5 to 6 and an arrow from 6 to 7, because an array, as you might know, does not include these pointers. So, what we have to do? We have to physically move this element 7 to 15 one step to the right, from 7 to 15, and when we have a space, then we can put this number 6 there. But here is the problem. To move this element, say in this case we had 6 elements that we had to move, we necessarily had to make 6 moves. There is no other way of moving the 6 elements one step right without using 6 moves. So, in other words, although in binary search we have taken log n number of moves to find the right place, to move this element we will need log n minus k, where k is maybe the place where the number 6 went. So, you have to make n minus k moves to move this whole set. Thus, in total we have runtime of n minus k plus log n. Note that in the worst case k can be 0, which means that we might have to move the whole set to the right, and thus the runtime becomes n plus log n. At the end, this technique 2 does not give us any advantage. So, when we want to insert an element into a sorted list, then we can call either of those two algorithms, which is say insert s comma x, and it would insert in runtime n plus 2. So, this gives us the algorithm for inserting an element into a sorted list. We will take a short break now. After the break, we will see how to use this inserting algorithm to get a sorting algorithm for a set S. Welcome back after the break. Before the break, we saw that we will need around n number of steps to insert an element x in a sorted set S. Now, let us see how can we use this algorithm to get a sorting algorithm. Just to recall, so in sorting algorithm we will be given a set S which is not sorted, and we need to sort this set S in an ascending order. For example, here we have this, we are given this set 1, 4, 2, 10, 5, 8, 15, 6, 13, 7, 8 and 1, and we want to sort them. So, to start with, what we do is that we take an element one by one, say in this case I have shown it from the right, and we insert in an empty list or empty set. For example, I take this first element 1 and we put it aside. Now, we take this next element 8 and note that this 1 there represents a sorted list, and all I want is to insert 8 into this sorted list. I can use any of these algorithms that we talked about before the break, and by doing so we can take this number 8 and insert in this sorted list. Similarly, now we will take this number 7 and again note that this set 1 and 8 is a sorted list. So, what we need is to insert this number 7 into this set, and again we insert it, and we keep on doing it. Again we can take 13 and put it in the set, and so on. So, the idea is simple. You take an element, you create a new array which is found initially empty, you put the first element from the right into that array, and you ensure that all the time that new array is sorted, and anytime you get a new element from the right, you take it and insert in the sorted array using the various insertion algorithms, and by doing so we will get a sorting algorithm. Let us see what the pseudocode of this algorithm. The pseudocode is kind of simple. We initialize an array T which is empty for now, and we start with the last element. So, we initialize I to be n, and while I is greater than equal to 1, we pick the ith element and insert it in the already sorted list T. Here we can use any of this insertion algorithm that we talked about, and we just call this insertion algorithm and keep on doing it. The correctness of the algorithm is almost obvious, because all we are ensuring every time is that the set T is sorted, and at the end of the algorithm all the elements would have been inserted into set T, and we have a sorted list which is T. The more tricky part is the runtime. Now, what is the runtime? Note that when I am looking at the first element, so that is when I have took the first element from the right and inserted it, then the array was empty, or the T was empty, and that time I had required almost no steps to insert it. I just took one step. Similarly, when I took the second element from the array, the last but one element, I just took one step to insert it, because that time size of T was 1, or in other words, when I is k, means when I am looking at the kth element, then the size of T is n minus k, because I have removed the n minus k elements and I put it in T, and when the size of T is n minus k, in that case the total runtime for inserting an element into this set is n minus k plus 2. This is from the insert algorithm that we saw some time ago. Thus, the total runtime is, say, for when I equals to n, it is 2, n minus n plus 2 is 2. When I equals to n minus 1, it is n minus 1 plus 2, which is 3, and so on, and thus the total runtime for this insertion for this algorithm is 2 plus 3 plus, and keep on going till n plus 1. N plus 1 is when k equals to 1, and if you sum it up, we get something of the form n into n plus 3 by 2. So, the runtime for this algorithm is n times n plus 3 by 2. For the space complexity, it is kind of clear that the space complexity is n, because we have to store the set T in a different place, and the set T will take n space. So, the space complexity will be n. Thus, to summarize this algorithm, what we have is that we have an algorithm that correctly sorts the list S. it has a runtime which is around n square plus 3 n by 2, and it has a space complexity of n. Now, the question is that do we have an algorithm that can do better, or rather can we somehow save either in the runtime or in the space complexity. Let us start with the space complexity. The idea is simple. Idea is that instead of using a different set T or different array T for maintaining the sorted list, we can do it at the same place. For example, let us see here, we have 8, the first one is fine. The second one, when you go to the second one, so we mark that one as 7. When we are at 7, what we do is that we, to indicate that we are at this state, we will mark the earlier one, which is 13 in this case, and mark this 7 as green. And now, for this green element, I will measure with the or compare with the next element, which is 7, which is 8 in this case. And 7 and 8, we do not have to swap or any such things, and we are done. Then we come to 13, and to mark that I have 13, I will make 15 red, and now I have 13 green. And the idea is that this red marking is just to indicate that I am at this place, which means that this set here anywhere in the right of this red marking should be sorted or almost sorted. And this green marking says that in this set, which is right of this red mark, this is the only element that is causing a problem, and I need to find the right place for this element. So, in some sense, this set right of this red is basically my original T in some sense, and this 13 is what I am inserting. Say for example, here, so 15 I have marked, and now 13 is the problematic case. So, what do? I measure 13 or compare 13 with the next element, which is 7 in this case. Since 7 is less than 13, I will swap it. Similarly, now still 13 is green, because 13 is the one that we are interested in. We compare 13 with the next element, which is 8, and since 8 is less than 13, we again have to swap, and thus we have this list sorted. Till now I had maintained that here it was sorted. To make the next move, what I will do is that I will say that okay, now let us put the marker to 8, and then let us look at this bigger set. So, thus I will make 8 to be red, and now we look at the set which is right of 8, where 15 is marked green, that means 15 is the number I need to insert. And again we do the same process, we again measure, compare it with the one right next to it, and if I find it small, then I swap, then again swap, and again swap, till again 15 goes to its right place, and done. So, right now again, as I pointed out earlier, that anything right of this red marking is sorted, and the red just marks that it is a cutoff point. Again at this point one may say that what to do? We can move the cutoff point at 5, make the 8 mark green, because 8 is the one that has to be inserted, and then we compare 8 with this next element, which is 7. 7 is less than 8, so we swap. 8 is the problematic case, we look at 8 and compare it with the next element, which is 8, and it is not strictly less than 8. So, we do not need to sort it or swap it, and thus the algorithm stops here for 8, and we have this set 7 to 15 which is sorted, and we have the cutoff point 5. So, this is the idea of trying to insert inside this set only. So, we do not create a new set T or new empty array, but we keep on acting as if we are working in a different array, but inside the same set. So, here is the very simple algorithm for this. As we pointed out, we start from I is basically the cutoff point, and at any point of time, and we keep on going till I is greater than 1, and when we are at this particular round of I, we look at we take j to be I, and we move the cutoff point to the earlier one. That means, the jth element is marked green that time, and then we have to insert this jth element in the right order, and thus we keep on measuring the jth element with the one right next to it, and if we find them less, we keep on swapping till it finds the right place. So, this is the pseudocode of the algorithm that I described using an example. So, I will not go into the details of this particular algorithm, but I leave it for you guys to verify that this algorithm does correctly sorts this list S. It is basically just a variation of the algorithm that I gave. This algorithm is what is known as the insertion sort. The good advantage of this algorithm is that the space complexity is constant, because we have not used any new space. In some sense, what is written here is slightly wrong. It is not exactly constant, it is in fact something like log n. The reason I said log n is, although we are not using any new space, but we are maintain the I and the j and such indices. Now, to maintain the indices, what is the size of the index? Index is the address of it, so which is log n. So, we have to maintain the indices, and that is why it is called, we can call the space complexity as log n. The runtime is same as the earlier one, which is around n square plus 3 n by 2. So, this algorithm has many other properties which are sometimes very nice. For example, this algorithm is in general very simple to implement. It is an algorithm that is used very commonly, and the simplicity of this algorithm is what makes it so popular. The second thing is that this algorithm works very nice in small sets. As we go along in the next few lectures, we will see some better algorithms, which is algorithms better than n square in terms of runtime, but still this algorithm is many times preferred when doing small sets. The third is that if I give you say a set which is almost sorted, means there is a few elements there which are out of place, but the rest of the elements are in a sorted list. Ideally, we would hope that to make this almost sorted list into completely sorted, we will not need much of time, and insertion sort exactly does that. It manages to sort the almost sorted list in a very quick time. It is also an online algorithm, that means if more and more elements are added to the set S with time, this algorithm can automatically be used recursively or repetitively to sort it without doing much extra work. And is stable, because if I have say 2 8s in this set S, of course, I can keep 1 8 like this or like this. I mean, which 8 I place first as such does not matter in a sorted list, but here insertion sort ensures that if a particular number is before another number and it is equal to that number, that will remain like that. So, this makes there is some properties of insertion sort. So, in this lecture we looked at an insertion algorithm. So, how to insert an element in a sorted list. Then we looked at sorting algorithm, one particular sorting algorithm, and then we improved it to obtain the insertion sort. Okay, with this we conclude this lecture. In the next lecture we will be doing more different sorting algorithms. Thank you.